Hi guys, my name is Jason Varghese,
My name is Maria Quintero.
and we'd like to present to you guys our DSP Advanced project, where we'll be recovering a corrupt audio file. So let's begin. Alright. And just to give you guys a quick overview, here's a breakdown of what we'll be discussing. Now let's get into this in a little bit more detail. Starting off with our introduction, um, just to break this down, pretty much there are a lot of topics in DSP that we could have covered, but we decided to go into audio signal recovery. We felt it was pretty interesting and at the same time a challenging project. What we did is we have audio files and where an interference was introduced, and what we wanted to do is find a way using DSP to remove these interferences. So moving forward, so with the objective and scope, now with taking those audio files, what's going to be involved is designing specific filters and isolating the noise and removing the corruption from the signal. Now with this, we're going to be using multiple techniques, and why we're doing this is because based on our proposal we presented earlier in class, Professor, you mentioned that you felt it would be better if we took a look at multiple interferences, and so we not only took that into account, we also decided that we would take a look at multiple approaches to solving these problems. So you can see in the second bullet point, we're saying that we're going to be using the DSP system toolbox, M-file creation, the filter design and analysis tool, FDA tool, and also Simulink. So these different approaches will be able to realize the filter with different techniques and different visual responses, and we wanted to see how this affected everything at the end of the day. Moving forward, okay, going into the project description, what we'll be doing with each signal is we'll be looking at the DFT, the discrete Fourier transform, and based on this, hopefully we'll be able to see the exact region of a disturbance in the frequency domain, and also after that be able to apply an FIR filter, a finite impulse response filter, that will be able to remove this specific disturbance. And based on each technique, we'll find what is the best way of removing this. For example, either the M-file creation, the FDA tool, or Simulink. All right, moving forward. Okay, our deliverables. What we'll be able to do is, like I mentioned, with each technique, we'll have multiple ways where we'll have the tool. We'll be using DSP toolbox. Now that's specifically going to be used for Simulink. We'll also have the M-file creation. We'll be using the FDA tool and Simulink, which will just give us a block representation. Now, with the original signal, we're going to have the frequency and time response of each, and then we'll have the desired filter. We'll be able to look at the magnitude and phase plots, so you can see exactly what is being filtered out to make sure it's not too excessive, and that was utilized with our iterations. Now, the output signal will give you guys the frequency and time response so that you can see, and actually Maria will be covering that portion, where you can see the difference where the original signal and then with it, with the time response, how the noise was removed. Now, in the end of the day, we'll give you guys a filtered wave file. You'll be able to listen and see that appreciably the noise has been removed. Now, okay, method of approach. Now, what we wanted to do is we wanted to realize a structured method so that with each of these signals, we have 3 different sound files. We wanted to make sure that we had the same approach every time, so that we'd have repeatable results, and we'd make sure that it was not unique to a specific situation. They're all the same. So now we're going to break down exactly what we did in our method. Okay, now method of approach. So with this, we use the wave read command. Now, what we are trying to do with this command is to completely understand our wave file, all the characteristics, because within Simulink and MATLAB, the following characteristics are very important to understanding how our audio file really was, in terms of the sampling frequency fs, the bit length with our convolution and with our algorithms and the math involved with each file, and x, the digital signal to process, and the samples per frame. Now then the next step was to identify the interference. Now, as you can see here, we have the equation for the DFT of each signal, which was then taken into account. And what we did is, as you can see in our actual presentation, there is a frequency of noise. So this is an example of what we were looking at. So you can see on the frequency response that the noise appears to be at about 1000 hertz. So now that we understood that, we went into our next step. Okay, now step 3. This is where we design our filter. As you can see here, we have the FIR output response equation, where BK is your filter coefficients. And from here we chose the different filters, your low pass, your high pass, your band stop, and also your different options, like for example your Blackman, your Kaiser window, rectangular, very many options, and we had to implement them using MATLAB, the FDA tool, and Simulink. And moving forward, you can see how exactly we did that. Okay, now here you can see it's a quick breakdown of exactly what we did, starting off with MATLAB. So here's a few of our commands. The first command was for the FIR filter. This is a stop, as you can see here, it's a stop band filter. And then after that, we also had the application of our low pass using a Kaiser window. And then using the FDA tool, which was another one of our approaches, you can see here all the different possibilities and all the different tools and selections you have. You have the response type, design method, filter order. You have your different options where Blackman was chosen for this specific example, and you have your frequency response. And also you can see here you have your plot, your frequency response. And then moving forward, you have Simulink. Simulink provided more of a block diagram where inside each of these blocks we had to break down and go through all our different specifications. So you can see here 16k hertz is chosen and all your other different specs. Now moving forward, you have your resultant signal, and although with the techniques we learned in class we were able to design a filter, we had to optimize this filter. Sometimes our band was too wide where it disturbed too much of our original audio signal. So pretty much this just breaks down how we had to do iterations. And as you can see here with our equations, we had the normalized disturbance which was found, and from that we chose our bands and we kind of just redid that. That was our next step. And then finally we provide you guys an output file, a WAV file. And so now we're going to break down and let you guys take a listen.
So let's start showing our results, and we'll start with our sound number 1, and I'm going to play for you guys the first sound with the noise in it.
The team with the best timing looks good. Tea in thin china has a sweet taste.
So as you can see, there's a high-pitched noise that if I show you the frequency response, you can see this very high magnitude peak in the 1000 frequency. And in the time response, you can see also this middle noise here is what causing that high-pitched noise. So that's what we want to get rid of. So again, like Jaisal said, we applied different types of techniques, and we got 3 different results. They are very similar, but with this kind of noise, we use a band stop filter. And so I'm going to play for you guys the result that we got.
The team with the best timing looks good. Tea in thin china has a sweet taste.
So as you can hear, the noise is gone and the message is pretty clear now. Of course, it's not annoying. So it's very noticeable here in the frequency response. We had that high peak here and now it's gone. And of course, in the filter time responses middle band here, it's gone as well as reduced, very visible. So you can audibly and with the plot, you can see that the noise has gone. So let's go with sound number 2. And you can see, first sound number 1, you can see a comparison of all the graphs and before and after applying the filter. So let's go with the sound number 2. This one has a distinct noise. It's very different. That's why we have to apply a different type of filter. So this is the noise for 2.
The team with the best timing looks good. Tea in thin china has a sweet taste.
So again, if I show you the frequency response, there's 2 high peaks here. And of course, we could apply a low pass, but we want to maintain this frequency, this range here, because that's part of the message that we want to maintain. And then in the time response, of course, you can see that noise here in the middle that we want to get rid of. And then for this one, like I said, we had to apply a cascade of a band stop and a low pass filter. And we did that with all 3 different techniques, and I'm going to show you the results are very similar.
The team with the best timing looks good. Tea in thin china has a sweet taste.
So again, you can see that the noise has definitely gone, and you can see in the filter frequency response, that these peaks that we used to have here are gone, and the noise is also gone. So that was a good implementation of a cascade of both filters. And in the time response, again, you can see this middle band has disappeared and the noise has been reduced. So I'm going to show you just so you can see the before and after results of applying this filter. So similarly with sound number 3, we have a distinctive noise. It's different from the other ones. So I'm going to play it for you guys so you can hear it.
The team with the best timing looks good. Tea in thin china has a sweet taste.
Now this noise was the most challenging just because it has more of a Gaussian noise that it's harder to get rid of without disturbing the message that we want to maintain. So for this one, I'm going to show you the frequency response, and as you can see here, there's no notable high peak frequencies that you can say, okay, that's what I want to get rid of. It's more of a embedded with the message, so that's why it's so hard to separate both without affecting the message. And in the time response, it's definitely obvious that there's a noise that we want to reduce. So for this, we apply a low-pass filter. We thought it was the best approach to get the best response and the best balance of getting rid of most of the noise without affecting the message. So I'm gonna play the result for you guys.
The team with the best timing looks good. Tea in thin china has a sweet taste.
So for this one, you can definitely hear some noise. It's definitely reduced from the original, but there's still some in the background. And in the time response, you can see here at the end some of that noise is gone, but it's really hard to get rid of it all without disturbing that message. And then in the time response, it's more obvious to see that result here in the middle. It's not as good as the other results as we got with sound 1 and 2. So again, you can compare the frequency and the time response before and after applying this filter. Okay, so for our results and discussions, we're going to talk about the 3 different techniques that we use to apply the filter and design it. So for our first one was our M file creation, and the pros with this is very versatile and it's very easy to troubleshoot, and we can go back and fix our errors and repeat it again as much as we want. For our cons, it requires a lot of knowledge from us and knowing all the commands and all the different capabilities that it has. The FDA tool, the filter design and analysis tool, it's really easy to use. It's visually friendly. We can see the plot right there and there when we were making changes. From the cons, the runtime is longer than the other techniques, and also cascading filters takes a longer time. For Simulink, this one's, again, it's very easy to use. It's very visual with the block diagrams. But the thing with this one is less precise than the other techniques, and also it lacks some of the complexity that we could apply with the other techniques.
Okay, now to go into conclusion, really quickly, a breakdown. Sound file 1, we had the 1000 Hz noise, we used the bandstop filter, and this was the most successful, as you guys heard. Then going into sound file 2, we had the 2 different disturbances, 2000 Hz and 4000 Hz. This is where we used the cascade. And then we had sound file 3, that was the Gaussian noise. We used the low pass filter, and it was the most challenging. And for that reason, as you guys heard, it was probably the least successful. Now, the lessons learned. There was definitely a ton of troubleshooting done. We had a lot of issues, a lot of errors that MATLAB would give, mostly with the M file creation, a little bit with Simulink. The FDA tool gave us the least issues. Filter optimization, like we mentioned, one of our methods was we did multiple iterations. And then, of course, the most challenging was the Gaussian noise filtering. We felt at the end of the day, a lot of the topics we covered in class might not have successfully covered this. We even looked into the textbook a little bit more. It didn't really cover this in great detail, how to optimize removing the noise. And then we learned the different MATLAB tools, DSP System Toolbox, M file creation, the FDA tool in more detail, and also Simulink. So this project was very valuable. We learned a lot. We really enjoyed this. And going forward, if you guys have any questions or comments, our email addresses are down below. Feel free to contact us. Also, our report is available for all of your review. Thank you very much.